Okay, we now have these equations, general equations, to deal with any any structural analysis involves these three always. Okay, so take a look. Okay, structural mechanics involves always three concepts. One is compatibility. Okay, number two is stress strain relations. Okay, number three is the equilibrium. So please remember this class always. A structural principle cannot survive without using these three aspect uh, of structural mechanics. When you say compatibility, we are referring to the Bernoulli's assumption. Okay, so it's not only Bernoulli, you can use other assumptions like Timoshenko's consideration on the shear distortion, etc. blah blah blah. Okay, so when you say compatibility, all the models you can see in books and in researches are available and are valid. Okay, so for this particular lecture, we will only be using Bernoulli's compatibility relation, considering plane sections remain plane uh, before and after bending. Okay, for stress-strain relations, this is just the Young's modulus of elasticity, which is defined on the basis of Hooke's law. Of course, in your continuum mechanics, this is extended into three-dimensional case, not only one-dimensional. And equilibrium, this is just simply the summation for forces equals zero, and summation moment equals zero. Okay. Normally we have three equations here and three equations here. That's why we have a total of six equations. But we can reduce this in case of one-dimensional, two-dimensional, and three-dimensional considerations. Okay, and to take note of the equations that we are going to use now for these three aspects or three uh, considerations in dealing with structural mechanics, we take note that in compatibility, we simply say that epsilon is proportional to your distance from the neutral axis. And that proportionality is given by the what? By the constant of proportionality, which is the curvature. Okay? So this is just a definition again of curvature with regards to compatibility. So for stress-strain relation, we know that concrete in compression is simply a function of strain. Okay, so this again will go to the graph of your concrete like this. Stress, strain. And we know that the tension of concrete is very small, such that this is assumed to be zero. But the tension for steel is big, so we have again to use Fs on the basis of the Hooke's law, that your stress is proportional to strain. Okay, so this is simply a formula using Hooke's law. Okay, for the equilibrium relation, we take note of the formula on the basis of an integral expression. So summation of forces equals 0 is simply stress times area. Okay, so your force here is simply the stress times area. Of course, the integral of dA is the total area. And for the moment is simply the force multiplied by a moment arm. Okay, so that's why this has a sigma y dA. Okay, so this is the force, okay, and this is the arm. So note that sigma is a function of epsilon given by the material stress strain curve, which is normally plotted in terms of an almost parabolic. So this is the actual, no? It's not parabolic class, but it looks like a parabola. So this is the actual. So where do you get the actual? Okay, you get the actual from lab. Okay. Okay, PCA, what PCA did is this one. Okay, so this is the PCA after it reaches a value somewhere at the peak, it actually becomes a horizontal line. Okay, so while the Hagnestad model, there's a drop. Okay, so these are models. So if you want to go make use of your own model, you just go to the lab and test. And that's a very good, difficult thing to do when you don't have the apparatus, the equipment to record your data on the process of the test. Okay. Okay. So what does PCA and Hagnestad gives us? It gives us a model, and there are a lot of modified models presented by other proponents. You can make use of when you deal with your research. In fact, you can introduce your own, no, model. Okay, but remember that this actual can only be plotted if you have the laboratory results. Okay, so this tangent line here simply states that your curve is actually below the angle in which the tangent line to the initial uh, point here at the origin is slightly higher than the actual uh, slope of the curve at a certain point beyond, okay, beyond 0. That's why we are not using the tangent modulus in this case. Okay, so the tangent modulus of elasticity is not used by the ACI. What does the ACI use? It uses a secant modulus. Okay, so where's the secant modulus? If you have a curve, the secant line is simply the line that is shortest, no? The shortest line or distance from one point to the other. So the secant line from here, maybe up to here, is the shortest distance, straight line there. Okay, so this is the secant modulus, which is fairly computed from 0 to, I think this is about 50% of your cylinder strength. Okay, so that's your secant modulus, in which the equation is given by the famous 4700 squared of FC prime. Okay, So, yun yung nakikita natin. We cannot use the tangent because the tangent is unconservative. It's bigger. Okay? Okay, so let's go back. At a certain point on the PCA, you will have here your epsilon c, which separates your elastic part with that of the inelastic part. Okay? Okay, it separates until it reaches the usable strain given again by the ACI, which is 003. So if you are not using the code of the ACI, then you change it to the other value. So if you go to a place where in the usable strain is not based on the ACI code, then you just look into their local code or national code kung ano yung ginagamit nila, and you can change your final formula on this basis alone. Of course, it's easier said than done. You have to really go into the history of how those code equations were derived. Okay, so the procedure for the determination of Mn simply boils down to the determination of the magnitude and the location of the stress block, or simply the determination of what you call the stress block parameters K1, K2, and K3. I don't know if this is the first time you heard this stress block parameter, because we are more concerned with Whitney's stress block. We are more familiar with this to yung tinuro sa atin noon tayo ay college. Okay? Yung ano ba yung Whitney's stress block? Yung beta 1 tsaka 0.85 FC prime. Yan yung mga stress block parameter natin. Okay? So, beta 1 has an equation, blah, blah, blah. And this 0.85 here. Okay? And when we talk of magnitude and location, we don't have problems with Whitney. Why? Because it's only a rectangle. Okay? Whitney is 0.85 F prime C times A times the width of the beam. Okay, so this is simply the volume of the stress block. And the centroid of the stress block is simply at A over 2. Okay, so this is simply 1/2 of the height of your rectangle. But we are not doing the analysis always using this stress block parameter, or else we will be confined again inside the box, into which we can no longer search for another or a new information about flexural behavior if we will just stick into this formula. Okay, so let's try to explore a little bit understanding on how an actual stress block is analyzed. Okay, so if we have here your actual stress block, which follows the shape of the stress path for concrete cylinder strength. So ito yung gagamitin natin, no? So hindi natin makukuha itong mga parameters K1, K2, and K3 unless again we have a test as an experiment. Okay, so ang gagawin natin, we simply make use of first maybe PCA, the Portland Cement Association, as the basis for our stress block parameters. So K1 has something to do with the value of your what? Your equivalent. Okay, equivalent, average, you can make it the mean, the average, the equivalent stress on the concrete that will represent that will represent your actual stress path. So that's K1. How about K2? K2 will represent the centroid of that shape. It's the centroid. And K3 will represent the equivalent area of a rectangle that will actually represent the area of your almost parabolic stress block. So we have the K1s, K2s, and the K3s. Okay, so what Whitney did is he made a model and then test. That's why Whitney's stress block is not a rectangular assumption. So when we were in college, we are thinking that it's an approximation of the parabolic stress block in terms of a rectangle. No, no. It is actually a one-to-one correspondence or mapping or transformation of your actual shape based on tests. That's why if you will say that Whitney is an approximate method on the basis of the shape, it's not. It is actually a transformation of the actual shape into a rectangular stress block based on test. Okay? So the word approximation is not a good word to define Whitney's stress block. It is a representation. Okay? It is a representative of the actual stress pattern because Whitney based the formula beta 1. Kaya niya dinerive yung beta 1 dahil dito sa graph na yan. Okay? So that is the reality about it. Okay, so let's not talk on rectangular section. We talk of irregular curve sections in general because I will not teach you how to deal with only rectangular sections now. Although, of course, these are not practical sections to use in actual practice, but this has something to do with your understanding on how continuum mechanics works and finite element analysis works. Okay, you call this mapping. Okay, so we will try to map any type of section into an equivalent rectangular section. So this is the actual coordinates in your finite element or continuum mechanics. This is the actual coordinate or the actual section, and this is called the natural coordinate. Okay, so a natural coordinate is a coordinate of choice that you use in order to facilitate your computation. So when you go to finite element computations, numerical methods, and continuum mechanics, you just combine them and you can do a lot of mapping or transformation. Mapping is just the same as the word transformation. Di ba pinag-aralan nyo sa continuum yan, yung transformation matrix? Okay. Ito, we don't need a matrix yet because we are just talking of scalar values. Okay, we are transforming y to x. Y is transformed to x. So what's the equation? Y is equal to k dx. Okay, so this is your transformation equation. It's not yet a matrix since we only have single variable. Okay, so it simply means that from an y coordinate, I get an x coordinate. Bakit ko ginawa ito? Because I want to make use of a natural limit or boundary. So if y varies from 0 to kd, my x will vary from what? 0 to 1. How do I get that? When I plug here y equals 0, my x equals 0. when I plug it y equals kd, my x equals 1. Okay? So, this becoming a natural limit simplifies everything. Okay? So, all those simple concepts you've been learning in your mathematics class will pave the way to your understanding on how to do a research. Because in the language of the master's degree thesis, you will not talk about simple terms. You will elevate or level up your note into one level higher, no? So you won't be using the simple tricks that you have been using in your college, or else you do not belong into the masteral level. Okay, so here when we solve beams, we solve it differently. We don't solve it the way the college sorry the college students solve your beams. Okay, so we are now mapping y to x because we want to convert the complexity of your actual coordinate to a natural coordinate, and then imposing the concept of the stress block parameter k1, k2, k3, which I told you a while ago, will give you now a more general formula for the moment capacity. Because if we can now get your C sub C, and I'm sorry I forgot the T here, so you can get your moment capacity on the basis of Mn is simply equal to Cc times, let's say, your moment arm, which is maybe Z, okay? Or this is also equal to T times Z. Okay, but Cc is the actual representation of the curve, not specifically witness representation. It can be a representation of another model, and the boundary of your section is no longer limited to only a rectangular section. Whether it's a curve, it's a T-beam, it's an L-beam, it's an I-beam, it's a circular beam, it's a parabolic beam. For as long as you know how to map your actual coordinate, the boundaries, etc., into a natural coordinate, then nothing is impossible. Okay? Kailangan nyo na lang dun yung programming because you have to deal with, of course, a lot of logic when it comes to programming. Okay, consider the irregular beam section singly reinforced with the stress block parameter K1, K2, and K3 as shown. So take note that the definition of curvature above is simply epsilon is equal to Py, will give us simply this epsilon is equal to epsilon C kdy. Okay, so I just substituted the value of phi on this, okay, because of my triangle like this. So if this is my phi, this is my epsilon C, and this is my y, I can make use of the definition of curvature in terms of compatibility alone. Okay, there are a lot of interpretation on curvature, and this is just one of the interpretation. And then we assume now the transformation in which x is equal to y over kd, so that epsilon now becomes, if I take this part here as my x, my epsilon now becomes simply x times epsilon c. So I now make use of a representation converting my strain into the x coordinate. Okay, you call the x coordinate a natural coordinate, and the process of changing the variable is called a transformation or simply mapping. In elementary, you call this the one-to-one correspondence. Okay? Ito yung matching type. Parang matching type. You match the figure on the left to the figure on the right. So see how logic simply evolves from your kindergarten level up to your master's degree level. So, pahirap lang ng pahirap. Pero pareho rin ang ibig sabihin niyan. Okay? So, from the figure above, the concrete compressive force may be obtained by simple integration. Okay, so this, I may now integrate this area or volume if I will multiply it by the width. Okay, so this is simply CC. So I just get the differential strip here. I have my differential C. Okay, if I integrate DCC, I will get CC. So from 0 to KD of your K1 FC prime multiplied by your function. Okay, so this is now the function. What is this function? This is the function based on the model curve. Okay, if I test it, let's say my test is scattered like this. Of course, I have to make sure that I represent this into a model. Let's say this curve is represented by this model. This is now stress is simply a function of your strain. So my equation for this line is simply the representative graph model of these laboratory results. Okay, from my stress strain diagram. And that's why my C sub C now here becomes simply the function. This is now the function. I just put outside the F prime C term to make use of a normalized value. Okay, kailangan meron akong variable to consider, no? So that is the ultimate compressive strength of the cylinder, Fc prime, is now multiplied by the function of the stress in terms of strain. Okay, in short, this is now representing your sigma is equal to the function of epsilon. And then I multiply it by the width, which is also a function of y, times the differential what? Width. Okay? Strip, I mean thickness. So this is now your differential area. We know that stress times area is a force. Okay, we integrate from 0 to KD. Again, this is difficult to integrate when you are using a computer because the computer cannot understand the what? An integration procedure in terms of actual values. We have to convert it into a natural coordinate, which is 0 and 1. Computers understand better 0, 1, 0, 1, 0, 1. In fact, all the logics that were converted from the low-level language is based on the binary language. Okay? So, ganun lang yan, no? So, ganun ka rin dito, no? So, para madalian yung computer mo, hindi mahirapan, gamitin mo yung natural limits. And we know that in our transformation, y is simply xkd and dy is simply dxkd. And the limit changes from 0 to kd to 0 to 1. Hence, your equation for your C sub C now becomes simpler in terms of natural limits. 0 to 1. Okay. You can use, those who are finished with numerical integration, you can use numerical integration on this, no? So what integration procedure? So the Gauss quadrature concepts, no? So you can use that. You cannot do it in math. You can do it in MathCAD, but the MathCAD is a high-level language. If you are actually programming a software to analyze such, like SAP 2000, STAAD, MIDAS, those softwares uses numerical integration. Okay, it cannot use MathCAD because MathCAD is already a process language. It has to be some languages that is capable of communicating with the system in Windows system. Okay? Pero ito kaya pa ng MATCAD ito. And I will not require you to do a software program. So I will just require you to do a simple problem computation. So you can use Excel, MATCAD, MATLAB, etc. Okay, so this is now your CC 0 to 1, so FC prime. So instead of having a sigma, a function of epsilon here, we have now a sigma, a function of x epsilon c. Okay, because epsilon is equal to x epsilon c. Okay, so you just put it there. Instead of having a b, a function of y, you get b, a function of x kd. Okay, and then why do we have to divide it by bo? Because we want to have at the end of our equation an area. What's an area? Area of a what? A representative rectangle, or simply an equivalent rectangle. While BO is simply the width of your representative rectangular section. So if I multiply it by BO, I have to divide it by BO there. So I simplified the formula, and take note that this part here, without the F prime C, is now LO. Okay? According to the derivation. So we have to compare this to K1, K2, and K3 later. Okay? Okay, hence your CC now becomes simply an LOFC prime BOKD. So it's just like very similar to a rectangular section which has a 0.85 FC prime. What is KD? KD is simply your C, okay, in your beta 1 CD. Okay, so this is a formula for rectangular section. Okay, but this is not a rectangular section class. It's an irregular section. We just mapped it to become a natural coordinate. That's why it appears to be a rectangle, but this is not a real rectangle. So note that BO is simply the equivalent width, the representative width, or simply the reference width of the beam. Okay, so the location of the compressive force CC may also be obtained by the same procedure, but this time we have the moment equation to use. So CC multiplied by YC is simply an additional Y there will just come out, and then of course we just add a Y there. This is the Y. Nadagdagan lang ito ng Y dyan. Tapos, yun lang ang nadagdag actually. These are all the same. Okay? Tsaka yung CC dito nadagdag. Sorry, YC. What is YC? This is the distance from the neutral axis to the level of your sigma. Okay? So if this is your parabolic block, this is your representative sigma, d sigma. Okay, so your y is simply from there up to this. It's a y of c. Okay, and this now will give you, upon integration, the centroid of the whole curve there. So we need the centroid. What they say emphasize there is we need the magnitude and the location to be the representative of the actual curve. Okay? So take note that this integration without the FC prime and without the BOKD there. Okay, so from here, KD So KD becomes BOKD squared here. BKD quantity squared becomes your L1 here, such that your C sub CYC is simplified into a KD squared. Okay, without this KD, hindi kasama to. Ito pinasa, kasama doon. Kaya squared ito. So, becomes L1, BO, and then FC prime. Ayan. So, matitira L1, BO, times FC prime, tas KD and KD there, squared. Okay? So, siya yung CCYC. And to divide your CCYC with C will lead to a YC equivalent to L1 over LO KD. Note that K2 is simply this formula here. Okay, what is K2 again? So in our figure a while ago, your K2 is the centroid. So this is K2 KD. Okay, K2 is the percentage of the depth from the compression fiber defining the centroid of your curve. Okay? Okay? So defining the centroid of your curve. And YC is 1. Okay, which is simply an L1 over LO of KD. Okay, so these are the parameters. Our target is to have K1, K2, and K3. But where are K1s and K3s? Asan yung K1 and K3 natin? But L1 at LO yung nakalagay dito. Okay? Okay, so K1 and K3 cannot be separated class. Because of the data gathered from the test results, it cannot be separated such that the LO del is simply equivalent to K1, K3. Yan. So, tandaan nyo lang ito. They are just, K1 and K3 are just the equivalent in terms of product of your LO. Okay? So, defined in terms of LO. So, where is LO again? So, LO is the coefficient on the CC parameter. Still, okay, so this one here. So, this is your K1, K3. Okay? Okay. So, let's stop at that point and entertain some questions.